For example, 2 to the third is equal to 8. Let me change to this. This is the exponential form. And here I will write its logarithmic form, exp for short for exponential, log for short for logarithmic. This in log form is the log of 8 to base 2 is equal to 3. Another example, 3 to the minus 2 is equal to 1 over 9. In logarithmic form, the log of 1/9 to base 3, write it small and drop it a little, is equal to minus 2. But on the other hand, for example, if we begin with the log of 16 to base 2 is equal to 4, write this in exponential form. That's the base. The 2 to the 4th is equal to 16. Again, if we have that 5/2 is equal to the log of 32 to the base 4, then 4, which is the base of the power, to the exponent 5/2 is equal to 32. I will now explain some of the laws and properties of logarithms. The first one is called the law of multiplication. Which is that the log of x, y, z to any base a is equal to the log of x plus the log of y plus the log of z, all of the same base a. It's important to not only see that the log of an extended product results in the sum of the log of each part, as you have seen me written it. We sometimes emphasize the both direction equality by doing something like this. The second is called the law of division. The log of x divided by y to base a in both directions is equal to the log of x minus the log of y, both of base a. 3 is referred to as the law of powers. Which is that if you have log of x to the exponent n to base a, that this is equal to n times the log of x to base a. And this is again to be understood as a law that applies in both directions. Since we have this equal to the log of x times x times x times x times x, as often as n is indicating. According to the law of multiplication, this is equal to the log of x plus the log of x plus the log of x for as many as there are, indicated by n. And if there are n of those, then it stands to reason that n of those is expressed as n of those. The properties, which I will explain, is simply an extension of the laws which I have just written, but they are worth special mention. The first case is that the log of x to base x to the nth is equal to n. Notice the base here is x, and this is a power, x to the nth. We can say that on the left side that this is equivalent by the law of powers n times the log of x to base x. Let's examine the log of x to the same base x. So anytime you see something like this, this is equal to 1. N times 1 is n. And this works in both directions. You will have occasion to use this. A second property worth emphasizing is that the log of 1 to any base x is equal to 0. If I write this in exponential notation, you can see that the base x to the exponent 0, and that is certainly 1. Third law, or sort of property I meant, is to observe that the opposite operation of logarithms is referred to as antilogarithm. I'm not talking about inverses or inverse functions here. The inverse to a logarithm is an exponential function. The antilog of something whose log is taken, say log of x, is equal to x. For example, write the following as the log of a single expression. Log of 7 to base 3 plus the log of 5 to base 3 is the expression that we want to write log of a single expression. We first have to make sure that the bases are the same before we can continue, and they are. And the law of multiplication in the opposite order to what it was given, we can say then that this is equal to the log of 5 times 7. Times 7 is 35, and the base is 3. Here's another one. Log of a to base x plus 5 times the log of r, I should have said, to base x. Once again, be sure that the bases are the same before you continue. You will notice that this problem is almost like the one I have just done, except for this 5, which is being multiplied by the log of r. If you recall, in the law of powers of logarithms, that this 5 can be written up here as an exponent to express the same idea. So this is the same as log of a to base x plus the log of r to the 5th exponent to base x. Continuing now with the law of multiplication, this is equal to the log of a times r to the 5th to base x. There you have it as the log of a single expression. Another example, 2 minus 3 log x to base 5 plus 1/3 the log of y also to base 5. Well, here we have an example where this particular term is not expressed as a log. And so consequently, there's no way those things can be combined as a single expression with this not being a logarithm. But if you examine one of the properties, you will have noticed that I can say that the log of 5 to base 5 is a 1. Recall that if you had the log of a number with the same base, this is essentially 1. So by putting a 2 in front of this amount that's equivalent to 1 has not changed its value whatsoever. So 2 times log of 5 to base 5, because of this 2 and the law of powers, we can express this 2 beside the 5 as a square. In other words, I can say then that this particular term is the log of 5 to base 5, with this 5 the base of this power, 5 squared. Okay, the rest of the parts will go there, and I will continue with this one here. Minus 3 log x plus 1/3 log y of base 5 and 5. Oh, what I wanted to do as well, while I'm looking at it, notice that 3 in front of the logarithm can be written over here as the exponent to x, and the 1/3 in front of log here can be written as the exponent to y. Now that we have set it up this way, take a good look and make comparisons. The bases are all the same. I can combine that into a log of a single expression. It will be log of 5 squared is 25. Since I'm subtracting here, then x cubed will be in the denominator. And since I'm adding, then we will multiply and write y to the 3rd as a fraction, or the cube root of y, whichever you prefer, and the base 5. We'll now do some calculator applications. Your calculator should have two functions, two key functions. That is the log key and the ln key. To determine such things as the log of 12 or the log of 3 or the log of 0.778 or the log of a number that large, you simply have to press in the calculator the number 12 and there's the log key. The log key gives 1.079181246. The log of 3 is equal to 0.477121254. For decimal 778, press log. The answer is equal to a negative number, 0.1090204. Try these on your calculator. Now, for this last number, you may not be able to get 12 zeros in. We can rewrite this in scientific notation, and so that is equivalent to the log of 3 times 10 to the 12th. According to the laws of logarithm, this is the same as the log of 3 plus the log of 10 to the 12th to base 10. Remember that this is the same as the log of 3 plus 12 times the log of 10 to base 10, and the log of 10 to base 10 is just 1. This equals 1. So whatever the log of 3 equals, you'll simply have to add 12 to it. We've already worked out what the log of 3 is, and so the answer is 12.477121254. Let's do a few for ln, and in fact we'll take the same numbers that we did there. What is the ln of 12, and what is the ln of 3, and what is the ln of 0.778? This time, use the ln key of your calculator and you should have it. So for 12, the ln is 2.48490665. Don't expect this to be the same answer where you're dealing with base 10. For 3, the ln is 1.098612289. For the ln of 0.778, the ln is negative 0.25102875. Now we will use the calculator to determine antilogs and antiln. Usually, where you have the log key, above it is the 10 to the x key. You usually have, similarly, above the ln key, you will find e to the x. So if we want to determine then the antilog of this, the antilog of negative 1.85, enter negative 1.85 and your inverse or second key. You should get 0.014125375. Try that on your calculator. Another example, find the antilog of 3.35. Put in 3.35, the inverse or second key, we end up with 2238.721139. Let's do this with the antiln. The antiln of 0.876, enter 0.876, the inverse key followed by the ln, and you have 2.401275369. Another example, the antiln of 7 is equal to 1096.633158. Evaluate the log to any base using the calculator. There are no other bases available on your calculator except for 10 and e. So that if we want to calculate the log of other bases, we are going to have to rely to process here. For example, let's say that we have the log of x to base b, where b does not equal to 10, nor does it equal to e. If y equals the log of x to base b, you will see that we can convert this to exponential form and write that b to the y is equal to x. If you take logs on both sides of this exponential expression or equation, it would simply be a balanced result where the log of b to the y is equal to the log of x. The left-hand side says that y log b, and that is equal to the log of x. Finally then, y is the log of x over the log of b. And of course, when I write log without a base, I'm talking about the base 10 here. And those logarithms are available on the calculator. B is not available on the calculator as a base. So if you take the number x and take its log to base 10, you take b as a number and take its log to base 10, then this calculation will give you what the log of x to base b equals. You see, you should memorize the composition of this calculation. Similarly, if you, this is, as I said, base is 10. Similarly, y can be found by using ln. The same thing will result. Ln x divided by ln b. So this is an equivalent solution with base e.